everyone. Thank you all for coming. Oh, we got a big crowd. It's really nice. I think these two need no introduction, but I'll introduce them. So let's just start. Well, Larry Mayer's got quite a bio, so I might take up some of our time. All of you know Larry Mayer and Ryan Calder. Please welcome them.
Okay.
Right ahead.
So it is a pleasure to be here, to meet some of you for the first time. But I think the biggest honor is that I understood that most of you know there's a spectacular operation going on in the Gulf of Maine right now with 2 Drixes operating at the same time. And I understood that for this operation, they brought the Drixes in for the spa. They brought the Drixes in, and the whole double Drix team are back here now just so they can come to the spa. That's a huge job. That's not really true, of course. It just so happens that that's a coincidence, and this is something we just were asked to do at the last minute. But we're really thrilled to be able to do it because it was really quite an exciting adventure. Kind of call it how I spent my summer vacation, really, because it was a very, very long adventure that Liz and Brian and I got to take from what used to be called Thule, Greenland, now called Pitifuk, on the Icebreaker Oden, and you'll see pictures of that icebreaker, Swedish icebreaker, in a moment. Leaving about August 7th, we actually left from Stockholm on August 5th and flew on a military transport flight, the single most uncomfortable military transport flight. Well, not many, but none as uncomfortable as this one.
And loud.
And loud, of course, and usually they're cold. You usually sit there freezing, and this one was like a sauna for 4.5 hours with a stop in Reykjavik, Iceland, and fortunately, the weather in Pitifuk was too bad for them to continue on, and nobody complained. So we didn't have to get, because it was just supposed to be an hour of fueling. We just get back in for another 4.5 hours in this sauna, where we literally sat facing each other and kind of knees interlocked in 2 long lines.
This is on a Hercules, a C-130.
Hercules, yeah, but it's a special Swedish configuration. I've been on a number of Hercs that have never been that small. And we eventually got to Pitifuk and took off on the Oden pretty quickly, heading up, and I'm going to point out some names of places. Nari Strait is this large area here. I'll talk about a polynya later. The polynya is an area of open water in the ice that stays open most of the year. That's up here. And we headed up eventually to our target, which is this place here called Victoria Fjord. Now, I should say that until 2019, no ship had ever gone further north into the Lincoln Sea than about that yellow line. And then in 2019, we were on the Oden, and I'll talk about that cruise to a place called Ryder Glacier, Osmond Fjord. In 2019, Osmond Fjord here, we made it that far. And this year, we tried to make it to the next fjord, and I'll explain why in a minute. And we did. And I should say that the plan was, if possible, to continue on when we were finished and head over the top of Greenland to Svalbard. And as you'll see in some of the ice imagery, we could not do that. And there was great disappointment because no ship had ever done that before. The Swedish icebreaker would have been the first. But at least I think in some of us, there was some happiness that the ice is degrading there terribly, but it's still holding out enough to prevent us from doing that. So I actually felt a little bit good on the inside about that part too. So this trip, like any trip to the Arctic like this on a major platform like the Oden, the icebreaker, was the result of a very long and competitive process within Sweden. It's run by something called the Swedish-Polish Research Secretariat. There was a large competition within Sweden for many, many different themes, as they call them, that they would devote the Oden to this summer. And there were a few, I and a fellow from UC Irving at the time, he's now at Dartmouth, Matthew Morgleheim, were co-PIs on that original proposal in Sweden, competing with other Swedish proposals, and eventually this one, which was called GeoEO, or North Greenland Earth Ocean Ecosystem Observatory, was the one that won out. And so that was chosen for the effort of the Oden this summer. Matthew, I, and actually some other American teams all put proposals into the National Science Foundation to fund this. And the National Science Foundation did not contribute at all to this. So they funded none of those proposals. But fortunately for us, NOAA stepped in, particularly the NOAA Ocean Exploration Group, and they agreed to fund our participation. So we were very grateful to them for doing that. The whole overarching theme about this was really to look at what we call the marine cryosphere, the interaction of ice and the ocean in northern Greenland, and really how that is changing in light of the changing climate, but most importantly, how that's impacting global sea level. And the reason we're focusing on Greenland is because over the last 10 to 15 years, it's the melting of the Greenland ice cap that is the greatest contributor to global sea level rise. Before that, the greatest contributor to global sea level rise was, anybody know?
Thermal expansion.
Thermal expansion, who said that? Thank you, perfect, yes. Thermal expansion of ocean water due to heating, but that's now been surpassed by the contribution of the melting in Greenland. That will not last, well, maybe 10, 20, 30, 40 years maybe, and then it'll be surpassed by, anybody know? Melting of the Antarctic ice cap. So those are the two big sources of rise to sea level. If all of the Greenland ice sheet melts, it would mean a 7.4 meter rise in global sea level. That would be more than catastrophic. Right now, the contribution is about 0.77 millimeters per year. We're focusing on the northern part of Greenland because it drains about 14% of the ice sheet. It holds about a 1 meter rise in sea level just from that northern part. But most importantly, crazy things have been happening up there of late. And that really started by looking at an area up here called Petermann Glacier and Petermann Fjord. Unfortunately, that fjord and glacier are named the same, and the next ones they're not, which makes it confusing. But in about 2010, the Greenland ice cap sits on top of Greenland. When it enters into the ocean, it does it usually through a fjord, these deep cut valleys that when the glaciers during the great ice ages pushed out, they carved these fjords, they've now retreated some. The glacier sits on the top of the ice of Greenland and then comes into the ocean, and it usually has what we call an ice tongue, a floating ice tongue that sits out in front of it. And that ice tongue acts as a buttress. It holds back the glacier from just calving icebergs and falling into the ocean and raising sea level. So that ice tongue is critically important in keeping sea level at bay, sea level rise at bay. In 2010, Petermann Fjord up here, which had a very large ice tongue, lost a huge hunk of it, followed in 2012 by another huge hunk of it. And that really started to scare folks. Why are the ice tongues going away? And so we proposed back then a cruise up there to see what was going on. You could see how far it fell back. An ice sheet, an ice tongue grows. It's like a river flowing all the time. It's moving forward. But in this case, the forward motion was more than compensated for by that failure of the ice tongue. And so we had an expedition on the Oden in 2015. It is singly the most beautiful places I've ever seen in my life, northern Greenland like this. And these fjords are spectacular. To get the scale of it, that's the ice tongue over there. This is entering into the fjord where the ice tongue had broken up and pieces of it forming these large tabular icebergs. And the Oden is in there somewhere. The Oden's a very large ship, 380 feet long. But there it is, just to get the scale of it. It's just absolutely spectacular. And again, just to see the scale of the feature, 1,000 meters high, the cliffs of the fjord. That's the ice cap up there. And here's the Oden And the Oden's probably 90, 100, almost 150 feet high in itself. So
6 floors of stairs from the mess deck to the science spaces. 3 times a day for 42 days.
Yeah, I live higher. 96 steps for me, at least 8 times a day, up and down. So our focus, our team, was working particularly with many of you, some of you know Martin Jakobsen from Stockholm University, who was originally a postdoc and a researcher here for many years, 6 years or so. He's now more than just a senior professor, he just became the vice provost of Stockholm University. And we've been focusing on the mapping components, the geophysical components of these cruises, which are all very, very multidisciplinary, as you'll see in a minute. You don't send an icebreaker up that far into the Arctic without making sure you take advantage of every possible bit of science that you can do. The Oden is equipped with an EM 122 multibeam. It has some EK80s on it, fisheries, scientific echo sounders, and ADCP, and an SBP 120, which is a sub-bottom profiling system that takes advantage of the multibeam transmitter itself, or excuse me, receiver, and uses a separate transmitter. So sub-bottom. It also carries a small vessel of Martin's called the Skidbladner, and it has a high-resolution system on it, and it has a workboat that we can put extra systems on. So our job again in Petermann was to map. That's what we knew about Petermann Glacier. You see the ice tongue here. Before we came back and we mapped quite a bit, got almost complete coverage, and you see spectacularly interesting geology, faults and things like that. But the most important thing from the perspective of what we were doing is that if you look closely at the multibeam, you can actually read the history of the glacier in the bathymetry. And you can see the striations, you can see where the glacier carved, you can see where the glacier stopped. We get these things called grounding zones. When the glacier stops, it's plowed all this material ahead, and then it'll retreat, move on. And when we combine that kind of mapping with particularly sediment coring and a bunch of other stuff, land surveys to understand sea level rebound or land rebound and things like that, and oceanography, we can put together a very, very detailed history of the dynamics of the ice sheet. Which is what we did. We can see different places where the ice sheet moved out, stopped these grounding zone wedges. We can date them because from the cores, you can date when all this happened from different methods. Another seminar I talked about how we date things, and then put together that history of how things moved in and out. And so that's part of it. That's the history over the last 15, 20,000 years of what's happened. But what's happening now, and this was what was so interesting, is when we combine the oceanography with the bathymetry, what we saw was that there was warm water. This is the 0 degree isotherm. So water above 0 degrees, which is not easy to find in the Arctic, below about 200 and something meters. And so this is the cold Arctic water, and this warm water is water that actually came all the way up from the Atlantic, traveled around the Arctic, and we didn't realize could get into the fjords. And so that warm water is coming in at about, say, 250 meters or so, and that's shallow enough that it could get over that grounding zone wedge, the sill, what we call the sill, at the outer edge of the fjord. And that warm water comes in, and we thought that's what's undermining the ice tongues. That's what's going on. So we thought we had a pretty good theory about that. And then we looked just 130 miles over to a place we keep referring to it as Ryder. It's really, the fjord is called Sherrod-Osborne Fjord, but the glacier is Ryder Glacier. And it has an ice tongue. And it was first seen by a guy named Volga Koch in 1917, because he did a sled expedition all around the top of Greenland, really quite remarkable. And he kind of sketched, I'll show you a picture of his sketch in a minute, of the ice tongues.
We should be clear, it was first recorded by him. There's evidence that it had been seen up to 4,000 years earlier by others.
Sure, yeah, he first recorded, thank you. And since then, we've had now, since 1989, we've had satellite imagery, and this ice tongue has been growing. So 130 miles away, one is being destroyed, this one is growing. So what's the difference? We call it a surge type glacier. The ice tongues growing out and out and out. And there's Lauga Koch's limit of the ice sheet. You'll see he had one in the fjord next door. And so that led to the next expedition in 2019. What's different about Ryder Glacier? And so we went there. The difference was, as I mentioned earlier, no ship had ever been beyond here. These are single soundings the Danes have done by flying out in a helicopter and cutting a hole in the ice or just putting an echo sounder on the ice, individual spot soundings. So we had some idea of the depths out here, no idea of the depths in the fjord. And that's a real challenge. No icebreaker, no ship captain is going to drive into a place, particularly a fjord, which tends to have these grounding zone wedges without knowing the depth. So it presented quite a challenge. It also presented a challenge because, so this is the Lincoln Sea, as I referred to before. This is where the last vestige of thick ice is in the world. Ice is diminishing terribly up there. The last multi-year ice is accumulated in the Lincoln Sea. And so that's why ships haven't been able to transit in there. In the Petermann expedition, it took us 7 days to get from Thule up to here. That's the Palinya. When we talk about the Palinya, I'll talk about that later, there. And then it took us to go these 55 miles. It took us 3 days because that's the heavy ice. And then we did get to, this is Sherrod Fjord, and we're able to work in there just fine. We have the map in there, just like we did in Petermann. We're able to see the bathymetry, same story, multi-coring, blah, blah, blah. Read the history, but this one was very different. Here we had an outer sill, just like we had in Petermann, that was deep enough to let the warm water in, but there was an inner sill up here that was shallow enough to block it. And so there was the proof. It's the Atlantic warm water that's causing this rapid degradation of the ice tongues. And if we can block it, we can slow down sea level rise. Good Corps of Engineers project there, build still. So there's Petermann letting the warm water in, Ryder not. Now Laka saw another fjord right next door, just 30 miles from Sherrod Fjord, and he measured an ice tongue back there in 1917. Satellite imagery showed that up to about 2002, there was still an ice tongue there, and then since then, there's been nothing. And so we thought this would be the opportunity for now to go to a place where there is no ice tongue, and let us see the processes, what's happening right where the glacier enters the water. And so that became the focus of this next cruise, the one that Brian and I just came back from, to look at those processes at the interface of the ocean and the ice sheet itself. Again, take a whole bunch of teams out there. I circled all the ones here that really depend on bathymetry, because bathymetry is such a key to it. And so we had the Oden again with all its sonars. We had the skid bladder and its sonars. But this time we also, because no captain, no sensible person will let a ship get right up against the ice face because that ice is calving, huge glaciers falling off, big pieces of ice falling off. So we needed to bring an uncrewed system. And so we, through the kindness of our friends at Seafloor Surveys, they lent us an echo boat, and even more kind, our friends at Norbit lent us a Norbit IWBMS, which has a curved array, and the idea was to slant that array so we could look at that ice front underwater. And we also brought an EK80 that we could slant sideways so we can look at what the melting process is. We can see the difference between fresh and salt water there. And the idea was to kind of get into this geometry with the ASV against the ice front, looking sideways, getting the shape of the ice front, the structure of it, but also looking at the water column data in the multibeam and the EK80 to look at freshwater plumes. So that was the plan. That's the Oden. You can see the Oden and a little satellite imagery here. We left that Palinya area on about August 12th, I would guess. We were here on August 14th. This is just one little segment where it took us 12 hours to get about 10 nautical miles, fighting our way through really, really heavy ice to try to get to Victoria Fjord. So that's the 14th. Here we are in the 16th, 2 more days later, and we're finally, this is Victoria Fjord, finally making our way there. And what you see here is what you do when you're going to an area that's never been mapped before. Take advantage of the multibeam and look sideways, steam along and see if it's all deep enough for you to go, and then turn around. And you just have to do these S-turns back and forth. Very slow process, but it's the only way you're gonna do it. No captain is just gonna go blindly into an area that hasn't been mapped, particularly as you get close to shore. And there are all little islets popping up here. It means that things get shallow. So at the end of the day, August 19th, it took us about 6 days, I think, to make that 100 miles, maybe less. And we got into Victoria Fjord. And it was totally covered with ice, but it was what they call shorefast ice. And that actually was fairly easy for the vessel to break. So we were able to break the ice and start our goal of complete mapping. The Victoria Fjord, slow but steady, did that fine. We look at the bathymetry there, what we found right away, I'll put a 400-meter plane along that bathymetry, plenty deep for that warm water to get into. But we were only in the top third of the fjord. If we look at the rest of the fjord, we got to map that far. The rest of the fjord, we just ran into a wall of icebergs. And you know, this is our breaking the ice. You know, we just couldn't get beyond them. We were stuck. And so we still didn't have the answer to the question, is there a passage for the warm water to get there, or to measure the warm water? And so you got to be innovative when these things happen. So our first idea was to take our echo boat with, we actually put another EK80 on there, a 38 kilohertz one, that'll get us down quite deep. And the idea was to fly it with the helicopter to any little open spot beyond the icebergs and make a depth measure, single depth measurement. And we tried that, and Brian and I and Liz had a nice little helicopter ride, but it turns out that the problem is you can't turn it on before. You can't let it ping in the air. So we had to have a way to make sure it only turned on when it was in the water. The Echo Boat and the Norbit in there can be turned on through a wireless transmitter. And so we have a wireless transmitter here. We have the other end in the PC controlling it in the helicopter. So the idea was to go out there, dip it in the water, and then turn it on and make our spot measurements. And it turns out that the prop wash and this little wireless thing was just not waterproof enough. So when they got wet, they stopped working. So phase 2 is take another EK80 just in a frame, but this time with a pressure sense switch, and dip it down. And when it got down, I think it was 5 meters it was set for. You just have to have the people in the picture.
That's the helicopter director looking very, very nervous.
Just dip it down, makes a depth measurement, and it worked. That worked fine. That really worked fine. It's really wonderful. Do the same thing from the helicopter, not at the same time, with XPTs. Drop XPTs from the helicopter. And so we were able to make a total of about 19 depth measurements beyond where we could map a bunch of XPT measurements. We were very, very constrained by helicopter fuel at this time, so we would have done more if we could, if we had more fuel to burn. But we got enough to be able to put together not a pretty multi-beam map, but at least enough knowledge of the bathymetry. The interesting part of this story was that the first depth measurement they made was over here, where we thought the sill would be, because here's the sill in Petermann Fjord, the one we had mapped in 2019. And we looked at the geology, continued, we said, well, there should be a sill over there, and sure enough, there was. And it came up to like 290 meters, I think was the deep, 297 was the depth we measured first, the very first one. We hit the shallowest point. And we said, oh no, our theory's all wrong, because this ice tongue is totally destroyed, and yet there's a big shallow sill there. But then when we got the rest of the measures, we saw there was a deep passage. So there is a passage for warm water, and when we dropped the XPTs down in there, we saw the Atlantic warm water in there. So again, this is another fjord that is going to melt fast, and did melt fast, but something more had to be happening here. So now we got that problem solved, but we wanted to really study the problems, the processes, the melting processes at the ice face. And our model, our picture, our experience of what the ice face looked like in Petermann Fjord, that was the edge of what was left of the ice tongue. In Ryder, that was the edge of the ice tongue. There are these kind of straight faces. You can go up there with the echo boat and make the measurements. Well, when we sent the helicopter down to look at where the ice met the ocean in this fjord, in Victoria Fjord, it looked like that. Nothing like what we'd seen before. It was like a nuclear bomb had gone off at that zone with all these giant pieces of ice calving and all this ice in the water called melange. This is what it looked like. It was just, I mean, we were shocked, absolutely shocked, and still don't fully understand. This is more than just the Atlantic warm water. We think it has something to do with the bedrock slopes and things like that, and that's what we'll be studying. But the bottom line is we couldn't take the echo boat. You're not going to put the echo boat in that to make
The echo boat is about that size.
to make those measurements. Yeah, quite spectacular. And so, and now I'll pass it on to Brian. I probably took way too much. It's okay.
We'll make it work. So we still wanted to do something with the echo boat. We'd be taking it all that way. We didn't just not do anything with it. So we had to try and work out something to do with it. But just wanted to start by pointing out this is not the echo boat's natural environment.
No.
So this is the echo boat in its home base in California, where it's nice and warm and sunny. It is physically, like I said, about that long. You just pick it up, one person each side, you can pick it up and throw it in the water. This is where it normally lives, you know, nice open water where the sun is shining and the weather is warm. So this is where we went, right? This is taken in Victoria Fjord. You can see the size of these things. I don't know if you mentioned it, but those blocks of ice that Larry showed you, they're about 30 meters high above the water. And if we assume that they're about 10 times that deep, you get an idea of just how much ice there is in those big chunks there. So we try and find some way around it. So we're going to talk about what we did and some of the lessons learned as well. And I don't pretend that any of these lessons are ground shattering, but we had to learn them again. So they may be worthwhile mentioning. So this is kind of our operating environment. What we decided to do was to look at what was happening around icebergs floating in the fjord, if we could. So there's the echo boat, scale, right? And this is one of the smaller icebergs that we were looking at. But remember, this thing is free floating, so it's moving relative to you. And you're on a small boat looking at it, and the small boat is drifting relative to it as well. And you're stood in the back in a survival suit with a handheld controller doing this, because normally what you'd love to do is you'd love to put down a line plan and then just say, hit the button, have it follow the line plan for you. But when you have things floating in the water, on which you will either ground yourself or destroy yourself, you can't really do that. So the only really effective way to do this is to drive by hand in this environment. Which then gives you a lot of interesting problems, which we'll come back to. Like, for example, the biggest one being, if you are standing at about water level plus 1.8 meters or so to your eyes, your sight line on this thing is relatively poor and very shallow. And so if one of these things gets in the way, it's very hard to see where you are. It's very hard to judge lateral distance as well. You can't really tell how far away you are, and in many cases you can't tell whether you're closer to you than the iceberg you're trying to avoid, or beyond the iceberg you're trying to avoid. The echo boat does have a front-looking camera on it, but of course the front-looking camera sends the data back to an ordinary PC screen, so if you're outside you just can't see it. It's just not bright enough. Lesson learned, if you have more time to do a good installation, you can get around these issues. If you're working with a vessel of opportunity, you probably need to do more of that to start with. Basic operations look like this. We were actually very lucky. We were able to use the helo hangar on the ship as a staging area for it. I love the Star Trek analogy, so I just took to calling it Launch B1. We could open the back doors and then sit it out in its stand, and then we'd pick the main crane, pick it from the shackle point on the midpoint there on a strap, and lift it off, and then fly it in the air. I sent this one to the manufacturers and they stopped talking to me after that. I thought it was kind of cool. I mean, use this in your advertising, right? And then Morton here, first mate, would direct it over the back, round the back of the ship, and then dunk it into the water where it was nice and free. And they have big long poles to push the ice out of the way from the back of the ship to let us get into the water. And then we'd either deploy on Moonen, which is the small boat, that workboat that the Oden carries, and just tow it from the back here. Or if we were close enough to the berg, we just put it over the side and control it from the ship instead. And there are pros and cons on that, which we'll talk about in a second. Actually tows remarkably well. The reason for towing it, of course, is just because there's a limited battery life. And so we wanted to tow it to position and then run it so we get the majority of the battery life. One of the lessons learned from that, though, is the battery life is not as fragile as we thought it was going to be. The expectation for it in warm water in California was about 4 hours. It runs on RC batteries, so big lithium polymer batteries about this size, 4 of them in the back of the boat. And it has twin props in the back, which are basically azipods, so you control direction and power. This actually managed about 4 hours, even in the cold water in the Arctic, which we were not expecting at all. It was way more resilient. And in fact, it can break ice as well, as long as it's thin ice. Liz made me feel very bad. She said it was like duck ice, meaning ice even a duck could break. Which I thought was uncharitable, because not only can it push littler bits of ice out of the way, any sort of skim ice on the surface, we learn quite quickly you can just break straight through and keep going. And it will part enough that you're not going to cause more
Sometimes it
scrapes.
slid over to the top of the ice, and that's a little scary.
We're going to talk about that bit. I carefully trimmed the video. Actually, for one point, I thought I was cursed, because every time Larry turned on the video, I bumped the boat into something. It was like some sort of horrible curse. We'll talk about that. We had one or two casualties, equipment casualties. We'll talk about that as well. But this is kind of the operating environment that we found ourselves in. This is taken from the ship. This is Moonen. I'm standing on the back deck. The echo boat is out here, and we're going this way round. That way round to go after an iceberg. The processing for it for the multibeam is relatively straightforward. So this is one of the steerable versions of the Norman multibeam. So we were able to, have the multibeam on, just looking straight down, and steer the beams electronically, port or starboard, depending which way we're going to the berg. You can see that when we have data, if depending on what the geometry of the iceberg is, this is the face of the iceberg here, once it undercuts there, all the beams this side, of course, are reporting noise, essentially. So you get a chunk of noise here, and there's noise there because you're basically shooting horizontally into the berg, so you get a bit more noise there. But the cleanup's not too bad, and if you have the watercolumn as well, you can do a pretty good job of working out what's there and very quickly generate yourself a point cloud. Of course, this point cloud, every time you do a second pass or multiple passes, it's moving relative to you, so there's issues involved in that. And it is more than we typically deal with in mapping bathymetry, a fully three-dimensional point cloud. It's not really like the sort of 2.5D approximation that we can make in dealing with most bathymetries, because the shape, particularly the shape here in the bit that's almost vertical, is super important. And so most of the tools that we've developed over years to deal with bathymetry, like seafloor bathymetry, don't really work terribly well. But a lot of the tools that are designed for LiDAR point clouds do. So we use Cloud Compare. Larry put this together. So we have the side view of the berg. This is a berg that was on the water line, used to be there, and that bit was under the water. This bit was out of the water, and then it toppled on its axis there. But you can see how the point cloud from the bathymetry matches perfectly what's going on there. And you can see all the nooks and crannies and folds and cuts in here where it's been differentially eroding and melting water out into the glacier, out into the fjord rather.
We should don't think that's all of what's underwater in the iceberg. That's all that we need.
Yeah, that's as much as you can see. Remember, this is a 400 kilohertz multibeam. I didn't say that. So we get down to about 40 meters roughly, and then we just couldn't see anything else because it was either undercut or we just ran out of range. So bathymetry is not too bad. The other sort of environment we found ourselves in was essentially an ice river. So this is an area this is actually Petermann Fjord, where fresh water has been flowing down the glacier and out into the fjord, and it's cut itself a channel. And the theory is that there's also a current under the ice. So it's basically eroded from the top and from the bottom, and eventually forms itself a nice little river there. And so you have freshwater melt coming in through the edges there, and we basically wanted to survey up and down in this environment as well. Pretty straightforward to do. It's actually easier to be in this environment because you're a little more protected. Putting out the CTD cast acts like a sea anchor, which also will hold you in place a great deal better, which is nice. So it's a little bit easier there, but one of the big issues is because you're visual driving, what you'd like to do is to stay a fixed distance off this axis here. Remember that shoreline is effectively moving. And so doing that just with Mark 1 eyeball is not a trivial process. But the data is pretty nice when you generate it. You can see the shape, you can see where we have shapes here. We know that when we see them there in the visual, we see them again here in the multibeam, and they match up really pretty well. So we were able to do multibeam surveys of it, and then also do EK80 surveys of it. Another lesson learned for us, I know it's one that Val has suffered from as well, is EK80s are really sensitive to noise, super sensitive to noise. Same issue you guys had with the drips and the electrical noise, exactly the same here. That's what these bursts are in the vertical there. What we found was that if you gun the engines, even the slightest bit, whole thing gets washed out completely. And we took the ship back into the launch bay and rewired, just rerouted the wires. And then it was fine as long as we went at full speed. If we went anything less than full speed, blanked out the signal again. As long as we went full speed, it was fine. So it's kind of hairy, you know, you're standing on the back of the ship in your survival suit with your fingers that you can't really feel because you've been out there for a couple of hours, with the controller, and you're driving it this way, and the only way you can drive it is full speed ahead. And then you have to do this while Liz is shouting at you in this year, go left, go left. It's an interesting challenge. But what we were able to see through all of that, of course, is what Liz thinks is freshwater discharge coming off. Now we could see it physically, you know, above the water as well. We think we can see it also in the EK80 data. And also, this is the watercolumn from the multibeam. You can see discharge coming out from the multibeam as well, from the various icebergs. So in that sense, we were able to meet our primary goals, which was detecting freshwater melt and looking at things like, you know, estimating, you know, where it's melting. One of the interesting things is that a lot of the models of how much freshwater discharge goes into the fjord don't account for water discharged at depth. The evidence is that icebergs discharge freshwater at depth, not on the surface when they melt. And it can stay at depth. And that's really not accounted for in current models for how much water comes into the fresh water comes into the fjord and what it does to the oceanography in the fjords. So in terms of lessons learned, again, getting it into the water, not a trivial prospect. This is actually getting it ready to go in the helicopter, but you can see the ice behind it as well. Just finding a space to put things in, particularly in that sort of ice launch, was not easy. But the ship's crew on Oden are just spectacular. They do this all the time. They're really good at it. Making modifications on the fly in the Arctic is not the easiest of things to do either. I'm on the deck. This is Larry kneeling on the dive deck, hoping, the rest of us all hoping he just doesn't take a tumble over the side in there. What he's doing there is, we had some passive acoustic receivers as well, which were coiled up on the front of the boat, and we're cutting the ties so we can deploy them and then tow them into position. And to do that, you have to cut the ties, take a lump weight, tie it on, put it over the side. There are probably better ways to do it. Again, best of opportunity is different from a good fixed setup, but there are tricky things to do that, which probably could have benefited from more planning than we put into it, to be perfectly frank. And the sightline issue is really kind of a big deal. When you're on the small boat, you can chase quite close to the echo boat, and so it's relatively easy to see where you are. Still doesn't stop you from getting pushed off. This is the little white post on the back here is a radio modem that we use for Wi-Fi connectivity. That's the second pair. We were surveying along one of the ice faces, and the wind picked up and pushed us straight into the ice, and not able to stop in time. the ice was overhanging like this, and it pushed us straight into the ice, and before we knew it, we were wedged into the ice. We managed to pull ourselves back out, but we left the antenna behind. So, not the easiest things to do.
The second Wi-Fi system.
Yeah, so it was the second one of those. First one wasn't my fault, that was the helicopter. That one was the one on the ice, the one we scraped off the iceberg was my fault. But we actually borrowed them from another group on board the ship, and we told them, kind of shamefaced, oh, we're really sorry we lost it. I said, oh, don't worry, we do that all the time. So being on the ship makes it a little bit easier, so we can go up 4 decks, and then we get much better viewpoint. As you can see here from the video, on where we are. You get an idea of the scale there. You know, you're driving by Mark on eyeball. And so by the time the boat gets out there where it can do something useful against this iceberg, for you physically, it's about that size. And so keeping good spatial context for which way you're going even is non-trivial, because if you lose concentration for a second, if it's, for example, as it was in one of the deployments, snowing, then you have to stop every so often and shake the snow out of the controller so it doesn't fry the controller that you're using. You can very easily lose which way you're going. And then if there's ice in your way, it can be hard to work out whether you're going forward or backwards until you hit the props. And if you hit the props, then you're committing to moving the ship and potentially hitting the ice. So, you know, being aware of that and being used to that is super important. Controls also end up being something that's really interesting. So this controller that they use, a standard RC model controller. And as I said, the props are aziprops, so you control direction and then thrust. All of the controls are on this controller here. Which means that if you want to change direction, you can't do it without being underway. So you have to have some thrust on, and then you have to pull slightly left or right with one thumb. And remember, you're in the coast, so you've got gloves on, and it's all on one controller, and it's really difficult then to change subtle changes in heading without also surging at the same time. It would be so much simpler if this one was control for direction and that one was control for thrust or vice versa. But for some reason they have it all in one controller. I have no idea why. So there are lessons like that we can feed back to the manufacturer as well. I mean, like I said, this is not its normal environment, so they may not be willing to make changes for it, but I think there's certainly experience there that we can feed back. And the last lesson learned was about endurance. Liz is going to kill me. I know there are pictures of me doing the same. I could use that, I just don't have one of it. This is coming back after our last deployment in the river. So the context for this is most of the mapping on the ship gets done overnight because everybody else who's on the ship need it during the day when they can see things for doing coring and small boat operations and everything else. So the majority of the mapping happens at night, so you want the most experienced people doing mapping on the night shift, which was Liz and me. But the echo boat, the small boats, can only go out during the day. So the way this unfolded was we'd wake up about 4:30 in the afternoon to be awake enough to have dinner, so you got some sort of food before you started. We then start shift at midnight and work till 8 doing the mapping shift, at breakfast, have maybe an hour or an hour and a half, and then launch small boats. And then we'd have to rally for another 2 to 4 hours on the water, and then recover, wash down the boat, get it re-prepped for the next deployment, get all the data off, archive all the data, and so on. So a small boat deployment like this could evolve into about 26 hours on your feet without sleep. We went intentionally light on our crew for this operation. If we were going out to do this in a sustained manner, I mean, you can do this for a couple of days at a time, then you need to have a break. Because once you've done that 26 hours, you catch some sleep and then you come back on for midnight again to do your watch again. So if we were going to do more than a few deployments, we did 5 in total. If we were going to do more than a few, we'd have to take more people. But then one of the big issues working in the Arctic is that getting on that ship is both difficult and expensive. Are we allowed to see how much?
$150,000 a berth. which is, to be honest, much cheaper than the normal way they used to charge, which was a percentage of the fuel charge. And so when we came back from Petermann and Ryder, there was $1 million fees for those. But they
And
decided-
every berth was taken.
Yeah, and every berth was taken and there were long waiting lists.
So we can't just say, we'll take another couple of people to give us a bit more slack in our schedule. And so like I said, you can do it once or twice, but if we were going to go out for a longer endurance event, that's certainly something we'd have to be considering as well.
Okay, I'll just real quickly, just because I mentioned that Polina, and it turned out, again, here's where you always got to pivot in the Arctic. You got to go with the flow and the ice, and since we couldn't go around Greenland, we came back and it gave us time to map in that Polina area, that area that is mostly open water for some reason, something to do with the oceanography. And it was really wonderful in a sense because there had been thoughts that there had been a huge ice stream coming in this direction, something called the Aleutian ice sheets. And it was all just speculated by geologists walking around the land, seeing indications. And we were able to quite clearly get evidence, these little moraines and things like that, that indeed it had. So just a few days of surveying could really turn around years of speculation and tons of arguments in the literature. And just to show you the power of seafloor mapping. And I think with that,
We promise you pictures of charismatic megaphors.
yeah, we had, because they were there and it was spectacular always. Just to show you, you can ask questions, I'll just flip through a few pictures. And what I'm gonna end with, the last picture, not the last animal picture, or mammal picture, will be one of the most amazing discoveries on this trip, which was a pod of 50 narwhals. Nobody's ever seen 50 narwhals that hung around for several hours. And you'll see a little footage of that. So polar bears. I will talk about this one just for a second. This was quite remarkable. This was already when we were heading back, all of a sudden, a raven landed on the Oden. Yeah, and for those who know Nordic mythology, in Nordic mythology, Odin, the greatest god, had two ravens, one on each shoulder. Munin, I don't know, I think Brian mentioned that small workboat on the Oden was called Munin. And the raven, this raven that appeared, landed on Munin. And the other raven is called Hugin, so everybody called this guy Hugin. So he would come to meet his Nordic mythology companion.
One of the biologists on board told us this is also the largest species of raven in the world.
Yeah.
They live right there.
I was up on the bridge and saw this big black thing, and everybody thought I was crazy. And then finally the bird landed on it. I thought this was just remarkable. What's a raven doing up in the Arctic? I guess they're not. It's not uncommon. It was probably uncommon for it to be offshore, but ravens have.
They live in both lands. It's just over.
Yeah.
Just slightly left of that picture stick.
Arctic fox, which was quite remarkable because they were, and we should have put the video in here. They were out in the middle of the ice, and they don't swim. And they're just amazing. They kind of they just jump and leap from one little piece of ice to another. And when the ice is, you don't think there's ice, it's thin enough that they'll like walk on water. And another polar bear, and the narwhals. Okay, if you have questions, just ask now. We'll let this play a little. No question? Yes, Mimi. Mimi was first.
For the Echo Boat remote communications, do you think it's big enough to fit an MBR?
Probably, yeah, the antenna's not that large. Yeah, that would be nice, certainly, yeah.
Depending on the power.
Yeah.
Because the power is limited a little bit.
That would give us a lot more range.
Yeah.
Yeah, that would be great, because we were nervous about going around the backside of the icebergs. We, in theory, could have done it, but if we lost connectivity, then what do you do?
The connectivity on the RC controller is much better than the Wi-Fi that you use to talk to the computer. So what you can do is you can set things up and then drive out of Wi-Fi range. And the range on the RC controller is about 3 kilometers. The time it goes out more than about 600 meters, you can't see it anyway. So you're kind of limited more by that than anything else.
Yeah, a couple of quick environmental questions. You're saying that the ice is so thick you can only make What, was there any concern about, you were in August already, so the sun's already proceeding. Was there ever any concern that you could get iced in?
Always, there's always that concern, but first thing on the captain's mind all the time. And so, first thing is that every icebreaker like that that goes up there actually is provisioned to winter over, if you had to. It wouldn't be good food, we'd be eating hot dogs, but it can, if it has to. We're actually in a little safer position with respect to provisions, if you have to winter over, up there than we were in our other ECS cruises up in the middle of the Arctic Basin, because we're not that far from land here. And what the helicopters have a limited range, but there's a whole series of fuel caches that every ship that goes up there, when you go up, the helicopter will go up, they'll put some fuel, helo fuel tanks. So they have a database of them. So they could find ways for medical evacuation or other things to connect up. We were close, I can't say close, we were several hundred miles from Alert on one side, and then the Danes have a military base at the other end of Greenland. So in a sense, this is a place nobody's been before, but in recent times, as Brian points out, we go out on land excursions there, you're constantly finding archaeological ruins of the Thule people,
Independence culture.
Dorset people, and the Independence people. 4,000 years ago, people lived there. Just remarkable. You talk about resilience, that people live in that climate.
Maybe the climate wasn't like that.
Well, no, it wasn't much better. There were changes. But they think about that all the time. And it was a really hard decision for the captain to make. He really wanted to circumnavigate northern Greenland.
Yeah.
And it shows how much they balance always safety and that ability.
Yeah.
And so, the way back, the ice was no thinner, but it was just a much, much shorter distance to traverse. And he knew he had enough fuel and enough capability to get there. And the Oden is a very, very nimble. It's very different than the Healy, which kind of brute force breaks ice. The Oden tends to always send out helicopter reconnaissance and plot out where all the little leads are and kind of twists and turns. It also has a very unique, a unique ice-breaking approach of getting up on the ice and using its weight, but most importantly, it has a flushing system to lubricate the sides and a locking system. Yeah. So it does that. So it's very, very nimble.
Just give you some context for it. They have 4 main engines. On 2 main engines, which is its normal cruising rate, it generates about 3.8 megawatts and will suck down about 1,000 meters an hour. It's a pretty big event.
Yeah, but the Oden is not considered a heavy icebreaker. The Healy is a heavier icebreaker than the Oden, and the non-working U.S. polar classes are even heavier icebreakers than that. None of them compare to the Russian icebreakers, particularly the nuclear ones. Yeah.
Would you consider on future expeditions using ROVs or even AUVs to get those tricky?
Yes, that's a great question. Yeah, so if we go back to this picture.
We actually had a team on board who were trying to do that.
Yeah.
And it didn't go well.
Yeah.
For various reasons.
An AUV, not an ROV.
An AUV, yeah.
Yeah, and with respect to an ROV, there is an ROV specifically designed for this at Woods Hole called Nui. And it had its first successful, it's been in the works for many years, but its first successful mission this summer in Greenland. And so this is it's a hybrid ROV. It's an ROV that goes down on a cable and then moves out like an ROV with a fiber optic umbilical. But the danger once you get on the ice is you're gonna break that umbilical. So it's designed, if the umbilical breaks, to become an autonomous vehicle and then come back to a coupling system that will then recover it. And it was quite successful this time. But I'll show a little picture. There was a team. The reason we got, there it is, Lulu they call it. It's a Swedish team that was designing an AUV design for underwater work, but they had a little startup problem. So
And I think we're gonna hear a little bit about that expedition.
Yeah, Alyssa's coming here next Friday? I
Yeah.
think. Yeah, so Alyssa will show you, yeah, I mean, it was really cool what they. Now, they brought a small ASV too. Ask her about that. Yeah.
To be fair to the team there, they had very unlucky evolution here. They packed up the logo and sent it on the ship. They're using a fins to do their motion sensor for them. And it was DOA. So they got there and it had been shaken or stirred or something, and their motion sensor was fine, and all of a sudden, according to the motion sensor, the ship went out the water, into the sky, and just kept going. So they had a number of equipment casualties that just limited their ability. Interesting.
They were a great group of people.
Great,
The reason we kept getting new wireless is.
Yeah, they had the spare parts bin that was much bigger than ours, so when the wireless got killed, that's where we got our spare wireless.
Are you familiar with some of the work Megan Wengrove's been doing? And I'm wondering, were you measuring gas content to determine, to see whether or not there were signals that suggested that, I think it's the pressurized gas bubbles that get released that then enhance the mixing at the surface?
Yeah, so Liz particularly is very familiar with Megan's work, and she discussed things with Megan before the trip. There was a whole other crew out there doing all kinds of gas work. So they weren't making measurements simultaneous with us. Our hydrophones were out there to actually listen to that, the sound of bubbles, which can be actually quite intense at a glacier front. But we weren't doing a similar type of measurement that Megan does. We were on a very small budget, and as Brian said, 3 people, because that was it.
And I guess this is a comment to the students in the room. Megan was a PhD student here several years ago. She's now an associate professor at Oregon State, but she did all beach processes stuff. But she came to enough of these seminars that she'd get really intrigued by questions and realize some of her boundary layer work may be relevant to the work that they're doing.
Yeah. And often the best contributions to anything are from people who come slightly outside with a new set or not constrained by preconceived notions.
So the bottom line is we may have data that would speak to that. It just, we're right at the start of the analysis of this data, which is also important to say. Part of this is a recruiting drive. If any of you are looking for a really interesting project with some really cool data, we have lots of data that is processed. Just another point.
Wow.
I'm curious about this data set. Where did this one come from?
That's from Svalbard. It's the same Norbert IWBMS that we used on it's actually on one of the little ASVs they brought.
Yeah.
It never got deployed.
No, it was in Kuningana. They did deploy it again. They deployed it for about half an hour on the prompt field.
Yeah.
In like 2016 or whatever it was that we went and mapped the tabular iceberg. We have a map that looks similar to that, and just like that one has like a line across the middle of it where there's no data, we had this very similar effect in the iceberg that we were mapping, and I just find it striking that it's so similar, but no idea if there's any.
Well, the icebergs often have an undercut, but the undercut, depending on the geometry, you should see that.
Yeah.
We did not have that. I mean, I don't think in any of our imaging. We're using what system we used?
It was Kongsberg EM3000.
2000, yeah.
Yeah.
I mean, it could be real. I mean, that was the thing. So we would image the icebergs in particular, but even the river channel. It's not really a river, but consider it the river channel. And as Brian said, everything is moving. And it is really noisy data set when it first comes in, and we have to clean it. And then I wasn't doing the cleaning. Liz was doing the cleaning. I was doing the cloud compare stuff, taking the 3D renderings. And I'm going, what is this real? What is, what's Liz's imagination? What's an artifact? And you don't know. But the intriguing thing is we made multiple passes, and each time the iceberg is moving or rotating. Doing both. It's drifting and rotating. But after all the processing, when you rendered it in 3D, you'd see all the these features that were identical on each pass. And that, I came in crying to these guys. I said, I can't believe it, it's all real. You know, the smooth areas were smooth on every pass. The ridged areas are ridges. You could see cracks each time. So it gave us a lot of confidence. And what we're working now with Tom Butkiewicz on is trying to see if we can do feature mapping and collapse them all to really increase the data density now that we have all these points to match in terms of the multiple passes of the, and then once we get really high resolution, we can really see the structure. Yeah.
You mentioned earlier you got a really comprehensive idea of the geologic history of that area. Is that published in a paper somewhere?
Oh, for this fjord, not yet, because we just came back a couple of weeks ago.
Right,
But yeah, I had some of the references up there, I think. Let's see. Yeah, so they're actually nature, I think a nature, let's see, that's a nature paper.
Okay, cool.
Yeah, and I'm happy to just send you that. And there are hundreds of the Swedes are remarkable on how quickly they get this stuff out. They have real pressure to do that. Their promotion system is totally tied into the number of publications. And so you'll see a lot of publications that have come from these cruises. Petermann probably out of that one, 55, 60 publications already. So I'm happy to provide whatever. Yep, Tom.
Sorry, was it possible to take a sample of the seafloor to identify what kind is?
Yeah, so we did. Each one of these programs, had with it a very extensive sediment coring process. Not from our little remote vehicle, but these are big major coring systems with a pipe. It's very hard to do in the ice, but the Swedes have really kind of figured that out. A lot of it has to do with the big fire hoses on the back of the ship and the big. Amazing thing, you can see a relatively large hunk of ice. Okay, all of here. A relatively large hunk of ice that's coming towards the ship or the wire, and with just a pole, with enough constant, you can actually push that piece of ice away. I was shocked when I laughed the first time I saw that. It was on the Healy. That they got the kid, they're gonna push these big pieces, and it works. It's really amazing. But so those coring systems work, and in the Petermann trip, it was really amazing. There, a group from the British Antarctic Survey went out onto the ice tongue itself and lived out there for several weeks, and they built a whole coring rig. It was the first time anybody took a core of the material under the ice tongue, because how do you get to that? So they drilled a hole through the ice with hot water, and then took cores down behind in the sediment, way back into the fjord. Yeah.
Between the coring and the sub-vol profiler, how deep into the seafloor were you able to take data?
Yeah, okay, so the deepest core in Petermann and in Ryder, those fjords, even though Ryder's not a fjord, I just was about 8 to 9 meters, and the cores are only rigged to 10 to 11 meters long. So the seismic penetration in Petermann and Ryder was on the order of 20 to 50 meters. In Victoria Fjord, where we just came from, there was no core longer than 2.5 meters, 3 meters maybe.
I think they got one that was a little bit longer, but it was further out.
Yeah, and there was virtually no sediment on this. It's a sediment, we don't understand this at all. This is something, the only thing.
I've never seen a coring team more despondent,
Oh, yeah.
because there's nothing for them to core for
And the sediment profile was just hitting bedrock everywhere. So these others are so filled with sediment, but the difference we think is that in Victoria Fjord, in these fjords, we got much further into the fjord, and in Victoria, we maybe were not at that place where, because under the glacier, a tremendous amount of material, sediments being washed out from the glacier. It had to go somewhere. So we're thinking it may be still stuck back further where we couldn't get to with the coring system and the seismic system.
Brian mentioned that it was challenging to pilot the echo boat from faraway perspectives and stuff, and I'm wondering, is there any reason why we can't just slap an off-the-shelf first-person view camera system on there and then wear goggles and?
No, absolutely not. And that's if you look at my notes, talk to Tom about.
We talked a lot
So
about
there
that.
is on the strength bar along the longitudinal axis, there is a camera right in the front. It's a little webcam. It's remarkably good. It's 4K cam. And it will, you over remote desktop, send that back to the laptop. The problem then is that you have a laptop screen which is that size, on which you have to have the control interfaces for the multibeam or the EK80 and that at the same time. And for environmental reasons, the laptop is inside the cabin, but for sightline, you need to be standing on the back deck on the dive plate watching what you're doing. And so unless you take your eyes off it and lose your spatial context and look down there, you can't see it. If you take it outside, it's too bright, you just can't see it at all. So we have the camera bit is easy. What we really want to do is to have some sort of head-up display so you can see it and look at it and then look at it and pilot. So that'd be a fantastic idea.
Yeah, we can do that all off the shelf.
Control, like a big Steam Deck.
Yeah.
Yeah, we learned a lot of lessons when we do this.
Or, I
Yeah.
mean, as long as you have a day-bright controller, day-bright display, because that's one of the big issues. One of the big issues being in the Arctic in the summer is it never gets dark.
Do we still have our actual vote?
Yeah.
Okay, so you could
We could test it.
Yeah, sure.
Exactly.
And we can offer all kind of suggestions about how to reprogram that controller and how to set up impromptu displays that would help with that stuff and not be hard to carry and all that.
Yeah. And then this one's, I was trying to make the point that, if you have enough time to do these things and you have it for long enough to do, remember this one was hired. Which is perfect, because then we can drive it like a stolen. And send it back with a few things and if nobody complains too much. If we had more time with the system and we were going to keep it for longer, absolutely, we would have stripped off their software, put on Project 11 and been much happier bunnies. Absolutely.
Okay. Oh.
Okay. Did you have other theory about the warm Atlantic water?
Well, I think we've been doing this long enough that we were pretty convinced. I think that after the first two cruises, we were convinced that that's a major contributor. I think what this one told us that, yeah, we see warm water in here, but the way this glacier ocean interface looked, this kind of nuclear disaster, says there has to be something else. Because the others haven't been reacting that way. And so we think it has something to do maybe with the slopes of the seafloor near where the glacier comes into the water, that you add the warm water source of melting plus a steep slope and things just start collapsing and collapsing. So again, we're just a few weeks back, so give us
The hard rock geologists that were mapping in that area claimed that there's a big difference between the underlying geological context in Victoria Fjord from Osborne Fjord, which is literally just over the mountains and down the other side.
30 miles away.
So in Osborne Fjord, there's a lot more sediment to be moved. In Victoria Fjord, they think that the glacier is basically sliding on bedrock. So that may also be a reason why we don't see as much sediment as well, and also why it's much easier for it to slip straight down into the fjord and just tumble over itself basically and be more disruptive. But to be determined.
Many questions. My first question. For the surveying on ice, I'm trying to do that. You talked mission to helicopters. Is that just purely putting a sound source as a single point?
From the helicopter,
One
but the helicopter was also used to do radar measurements on the ice as well. One of the teams from
a different team, yeah.
Different team was doing. Nina's not with Stock. She's not. Yeah, okay. So Nina Kirshner, one of the other PIs, was doing radar ground penetrating, but ice penetrating radar to try and measure top and bottom surfaces as well. So we did that from the helicopter. But the echosounding piece was just single point measurements.
Because sometimes the ground penetrating can see the water pretty well, but it depends
but that's not what they were interested in. They were on land when that was happening.
They were looking at the thickness of the ice and the bedrock, and I think that's why some of the answers to the questions about what the bedrock is doing, are the answers from that ground penetrating radar. It's not ground penetrating.
Ice penetrating radar.
It's ground penetrating radar system put.
But then one of the big, like Larry said, one of the big issues that we had with the helicopter is even though the ship took on more JP1 or JP5 or whatever it is than they were legally allowed to take, they actually took on much more than they were in. Because it took us so long to get into Victoria Fjord, they had to do lots longer transits with the helicopter, and so we burned a lot more fuel than we had burned on previous expeditions. So by the time we got to Victoria Fjord, we actually had, crisis meetings about spirited exchanges of views about who should get the limited amount of fuel that we had left. I was told once that the PIs would have a meeting every evening at 7 o'clock after dinner. And I was told the PI meeting about what science was meant to be done the next day would take maybe half an hour. Then the debate about who got the helicopter fuel would take another hour after that. Because it was, everybody was trying to fight their corner.
You saw those lists of teams. There were teams that wanted to go out every day on the helicopter and collect wood. Driftwood it tells an amazing story in the Arctic. Where there's driftwood implies that there was no ice. Where there isn't driftwood implies there was always ice covered. They can identify the provenance of the driftwood. And there's a whole archive of different. They read the tree rings, so you get the age of it and where it came from, so you can put together current history. And now they're doing on shrubs, they're doing tree ring dating and getting a really, really high resolution. So there's the driftwood team, there's the lake coring team, there's a team that goes out there and finds lakes and then cores in lakes by hand to collect the DNA records, looking for when the muskox came and the muskox went, and when the wolves came and wolves went, and when people came and people went, and you can all find that.
That's the mystery of the independence culture. So there's 4,000 years before present. They followed the muskox into Greenland, and they did not fish, apparently, as far as anybody can tell. So they lived on the muskox. So whenever the muskox show up in the record, you expect humans to follow. So you can tell by the DNA, the environmental DNA in the cores when the muskox showed up. But then they just disappeared. And nobody entirely knows why. The working hypothesis from the researchers that are there is that the muskox population collapsed. Probably because the independence culture people ate them all.
No, it's a direct.
And then the question that's unknown is, did the independence people then all die out? Or did they leave and do something else? Or did they start fishing? And nobody really knows, and they're hoping to try and make that, find out what that story really is.
Because the next culture is the Dorset and the Thule people. The Thule people are still there, basically. That's the native Greenlanders, or descendants of the Thule people. But they developed a maritime culture, so they lived off the ocean, not just amongst them. But the independence people were strictly inland feeders.
Dorset ate them all.
Don't laugh. I'm not going to go.
They measured this by measuring DNA in lakes that have been around since the last glacial maximum. Which, if you're not impressed by that, the doors over there, you can leave, because that, to me, that's like black magic. It's the most remarkable thing.
Okay, thank you all.